Welcome to the presentation of the topic Software-Assisted Clamping Point Classification and Position Optimization for the Efficient Flexibilization of Car Body Fixtures using Mathematical Geometry-Based Search Algorithms. My name is Rayk Fritzsche and I am Head of Group Systems for Body in White and Assembly at the Fraunhofer Institute for Machine Tools and Forming Technology in Germany, Chemnitz. At first, let me say something about the motivation. In the last years, we have increasing model range. Every OEM offers different model variants for each possible target group. We have new materials and new technologies which enables short-term innovations, and the OEMs want a rapid market launch for competitive advantage. The consequences are a rising model diversity, decreasing lot size of each single model. We have shorter model production cycles. We have a reduction of the planned startup times. We have shorter return of invest times, and often there are underutilized production lines. Our approach is to develop a flexible car body fixture system, and with such flexible car body fixtures it should be possible to produce over 10 different car models on one line without changing the fixture. We also include a model change in production cycle, and the process included new model startup. For the development of such a flexible fixture, we have to do some analysis and optimizations. The single components are fixed in fixtures using different tensioners, and the parts to be joined are held at clamping points by contour pieces on each side. In the picture we see a simple fixture and a simple tensioner with one clamping point. The clamping point consists lower contour piece which works as a support, and the upper contour piece which works as a pressure piece which is actuated over the clamping arm. Sometimes there are also tensioners with more than one clamping point. Here in the right picture we see a tensioner with 4 supports and 6 pressure points. And we have to realize high quality requirements, the geometric accuracy. Therefore we need contour piece positions that are precisely configured to 1/10 of a millimeter, and also we have the pressure pieces are accurately adapted to the component's contour. To fix the components of several different vehicle models on one fixture, it is necessary that each clamping point can be positioned, and also that each individual clamping contour can be adjusted if needed. So we have to resolve such multiple clamping points, and we have to simplificate the clamping contours if necessary. In this example we do this that we repositioned the clamp gripping on the outer and inner flange areas of the window frame, which is shown here in the middle picture, because these are the areas of flat contours, and so we have flat clamping contours. Also we have to divide such multiple clamping points, for example, into 2 single clampers with 2 single clamping points. And you can see here in the right picture clamping point 1 at the inner flange, and the clamping point 2 the outer flange, and the repositioning of the clamping points between the several parts we can do with our developed kinematics. In general terms, the clamping points are primarily located at an empirically defined distance of 30 to 50 millimeters from the joining points. The joining points are preferably placed within the flange area of the parts, and depending on the parts, the majority of the clamping point contours are flat, but also some are always uneven and unflat. For a software-based processing, at first we do a classification of the clamping contours, which is shown here in the table. So we have divided the clamping contours into 4 contour grades. Contour grade 1 for flat clamping contours, contour grade 2 for 1D shaped clamping contours, contour grade 3 for 2D shaped clamping contours like a ball, and contour grade 4 for complex and 3D shaped clamping contours. After that, we do in grouping and in categorization in terms of the constructive solutions and an assignment of specific contour piece solutions. So you can see that the contour grade 1 is furthermore divided into 2 groups. The group 1 are only flat clamping contours, which are plan and parallel, and the group 2 are flat clamping contours which are tilted up to 20 degrees, and all other contour grades are grouped in the group 3. And you can also see that we have some examples for the contour piece solutions. The group 1 can be realized with face milled contour piece. The group 2 contours can be realized with such toggle locators, and the contours which are complexer in the group 3. For these clamping contours we can use such changeover systems or such examples of pin cushions, or also we do some developments at the Fraunhofer Institute with adaptive polymers. If you have a look to the distribution of the clamping points after our classification, we can see here in the picture there are some differences between different models, and we can say that often newer fixtures often consists more three-dimensional shaped supports and pressure pieces, which is shown here in the picture B. So the dark blue contour clamping contours are 3D shaped, and we need flexible contour pieces. And this depends on innovative part structures, modern manufacturing options, or cheaper manufacturing costs of the contour pieces. So a large number of such adjustable contour pieces need to be used if we want to create a flexible fixture for these two parts. So the flexible fixture is very expensive, complex, space intensive and prone. So the aim is that we get a flexible fixture which is as simple as possible, versatile for different vehicle models, and also with a high availability. So therefore it's necessary that we used simple clamping contour and simple supports. So we do an automatic reconfiguration, or also we can do in initial definition with the simplest possible clamping contours with our software. The developed software do it first and read out of the clamping points from the design data with the corresponding coordinates. Then the software do an analysis of the clamping point positions with associated clamping contours. And the software do a calculation of the clamping contours geometric specifications, and the results are the height differences, the component thickness and the contour grades. The method to determine the clamping contour is at first the generating of concentric circles around the clamping point. And therefore the number of the circles and the largest radius can be selected in the software by the user. Then there's a projecting of the circles onto the component surface. After that we divided the circles into 40 subsegments by radial lines, you can see in the picture. And after that we do a diagonally dividing of the subsegments, and so we get a mesh of nearly triangular segments. After that, it's a calculating of the high values of each intersection point projected onto the component in relating to the circle center, and the intermediate spaces are interpolated, and after that we get a graphic representation on request like shown in the picture. In this example, the zero plane is the XZ plane of the part, which reflects the component's main direction of extension. But it's also possible that the software can determine the mathematically optimal reference plane. In the next slides we see some extracts from the software tool. Here we can see one clamping point after the automated analysis of the clamping contour with the defined parameters. With the software we can also load parts from different models. You can see on the left side we have here loaded 4 parts, but only shown the blue part. And the right side we have a listing from all clamping points and also from the welding points. And additional features of the software are an automated grouping of the clamping points and calculating of the distances between the clamping points of one group, and an automated alignment of the different parts with different optimization criteria. Here we see the clamping point 10, which is not optimized. It's the original clamping point and with indefinable limits. Here, for example, with a search radius from 30 millimeters, the software displaces the clamping point until a simpler clamping contour is found, and the target is a contour grade 1. So in this slide we see the optimized position, and with a correction of about 20 millimeters in Z direction, a clamping point with a plain clamping contour like grade 1 could be found. At the lower, in the lower side of the picture you can see the full coordinates of the clamping points. Now we enclose the green and the yellow part, and we see clamping point of group 10 of the 3 parts. And the yellow and the green clamping points are not optimized and have a contour grade 2. After the optimization, all clamping points have a contour grade 1, and we can also see in the right lower corner of the picture the maximum distances between the 2 points are here after the optimization by 54.3 millimeters. Before the optimization there was 86 millimeters. And also the sum of all distances between all the 3 points could be reduced from 165 millimeters to 135. So with this optimizations also the travel paths of the kinematics could be reduced. Furthermore, the software can show us all the profile cuts of the different clamping points and the specific distances between the points. In addition to the automatic optimization of the software, it's also possible to do some manual adjustments and shifts to the clamping points. In the summary, the software shows an overview of all clamping points in relation to the different parts. We can also see the alignment of the different parts together. The numbering of the clamping points can be adjusted by the user, but also the software do this automatically. The table in the right upper corner shows the contour grade of every clamping point group, and the decisive factor for the contour grade of one clamping point group is the most complex contour within the group across all the components. Here in our example, across the 4 components, red, green, blue and yellow. In the table we can see at the clamping point 1 and 2 a contour grade 0. This is because 1 and 2 are not really clamping points. 1 and 2 are positioning holes, so these 2 areas don't have a contour grade. And you can see all, nearly all clamping groups have a contour grade 1. Only the clamping group 15 and the clamping group 24 have a contour grade 4, and so for these 2 clamping points and clamping groups it is necessary to realize a flexible contour piece, and all other clamping points can be realized with a toggle locator in the flexible fixture. So let me give a little conclusion at the end. With the software tool enables an automated and model spanning classification of the clamping points. Within limits defined by the user, the software can optimize the clamping points in such a way that the simplest possible clamping contour can be realized. This allows an enormous simplification of the clamping fixture, especially when implementing model flexible fixtures which can hold components from several different vehicle models. And the calculated data and images and diagrams can be exported as an Excel document via VBA interface. Yeah, and the next steps for further developments, it should also be possible to integrate a new component from another vehicle model into an existing device configuration. So thank you for your attention, and goodbye and have a nice day.